Okay, so we're going to go ahead and get started. You guys had your assignment sheet, and we are going to be doing the electromagnetic radiation spectrum notes today. That is coming later. That's the handout you guys got from your group leaders. Right now, we're just backfilling some notes. So if you remember from your composition notebook, if you go to your number 10 page, should be stapled in, you have a page that looks like this, right? And we said that we were going to go ahead and put this information on your next test, so that's what we're doing now. We're going to take notes on this page. So find that page, it's your number 10. And this part of your paper on the back side where it says draw and label the Earth's layers, we are going to do that on a separate sheet of paper. So you can cross that out, and you can use that white space to take additional notes today. So all your notes can be on these two pages. If you need extra space, because you might, depends how big you write and draw, you can always use that white space behind your stapled in paper. So you should be able to get all your notes there on page 10 for today's lecture. Okay? So then you have your density lab. Your assignment sheet is going to be going on your page 12. So the assignment sheet for this unit will be going on page 12. And then you have your number 13, atmosphere and a balance. You have your density notes on page 14. If any of you missed density notes, there's a copy on a nail in the back of the room by the boat in the water. And so you can look at those notes if you did not get them, if you were gone or whatever. And then we'll be doing the assignment I gave you today, number 15. Okay? Question?
Wait, what's number 12?
Number 12 is where you're going to put your new assignment sheet for the unit. Okay? All right, so let's go ahead and get to that number 10, and let's go ahead and get started today. Last thing is remember that you guys have a quiz over the density section that you can add points back onto your test score on Monday. Don't forget, it's a great opportunity for you guys. All right, so here we go. If you look at your note page, you see some blanks here, so we're going to talk about these. So when you have fusion in the sun, this is a review, you should know this. Fusion in the sun, fusion, is the source of external energy in the earth. So remember that, S-U-N. That's when you have hydrogen plus hydrogen combines or fuses to form helium, and that occurs in the sun. Now energy travels through the electromagnetic waves, and wavelengths determine the type of energy. So we have all these waves coming from the sun. And depending on the frequency or the wavelength, it will determine what type of energy we have. And we'll get into that in just a few minutes. The higher the frequency, the higher the energy. So that's a direct relationship. Higher frequency, higher energy. So that's a direct relationship. So the opposite would be true. Lower frequency, lower energy. Okay, so that's a direct relationship. So now we're going to switch over to the electromagnetic spectrum and kind of explain this. You guys have pictures here. You can see that wavelengths are measured in distance, 10 to the third, 10 to the minus 2. And those distances is what determines the type of electromagnetic wave there is and what type of energy we have. So that is what all these numbers are. It's just the distance, 10 to the minus 12. Okay, that's really small. You can't see it. And there could possibly be other wavelengths out there and other types of energy out there that maybe we haven't discovered yet. So it is possible. Okay. I need your name written on that, please. And then you can take that 1/2. Thank you. So right here, we're going to go ahead and get into what is the electromagnetic spectrum. Yeah. That's from today? Oh, I thought you gave me yellow sheet. Okay. So right here, let's go through what EMR stands for. EMR is electromagnetic radiation. EMS is electromagnetic spectrum. Okay? So sometimes we'll just start saying EMR, EMS, and that's what we're talking about. So let's look at these waves and what are the different parts of the wave called. When you have a wave that goes up to the very tippy top right before it starts to drop, that is the crest. So you can see on my drawing I have 3 crests. 1, 2, 3. The very bottom, it dips down right before it goes back up, is the trough. And you can see how many? 1, 2, 3, 4 troughs in my drawing. So you need to know the parts of the wave, so you should be taking notes. And you need to also know what a wavelength is. So here, from the top of one crest to another, that is the wavelength, and it's measured in distance. So some kind of meter. The next thing we're going to talk about is frequency. We just mentioned frequency, high frequency, high energy. What does that mean? How can you see that when you look at wavelengths? We're going to move up just a little bit here. We're going to start talking about frequency. Does everyone have the parts of the wave? Okay. So here we have frequency down here at the bottom. And you can see that I drew these wavelengths, and there's different frequencies here. Some frequencies are longer, and some are shorter. So what is a frequency? How they measure that? The frequency is the number of wavelengths that passes a given point per second or per unit of time. It could be a nanosecond. That's really small. So just by looking at these frequencies, you could see different types of energy. So here's a lower frequency compared to these crests are really close together. That would be a higher frequency, and here is a lower frequency. They don't necessarily go higher. That was just something I drew really fast. But you can look crest to crest to crest to crest, higher frequency, crest to crest, slower. It would go by that point slower. So I'm going to go ahead and move these wavelengths through a given point, and I'm going to say dot or beep as it passes each crest, and you can kind of hear it and see it. So we'll start, here's the point right here at the bottom. So we'll start here. I'm going to try to go at the same speed, and I'll beep at every crest. So beep, 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 beep. So did you hear the slow and the fast? Okay, so that's how you measure frequency, and that's how you see it when you look at a wavelength. Okay, everyone has that? We're good? All right. So next, where do these waves come from? The sun. So when you have energy in different wavelengths in the electromagnetic spectrum, electromagnetic radiation, that is coming from the sun. So we get these wavelengths from the sun. So thank you, sun. when we're looking at frequency and we're comparing it to the wavelengths, and I went ahead and drew it so I can see it. So an increase in frequency, beep, 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 is a decrease in wavelength. The wavelength distance is getting shorter. That's an indirect relationship. As one thing goes up, the other thing is going down. As one thing is increasing, the other thing is decreasing. So you get that thumb. That's an indirect relationship. Then you can always say the opposite is true. So as you see a decrease in frequency, there's an increase in wavelength. And you can see that here. Beep, beep, beep. So when you guys look up here at your wavelengths, you can see that, is this an increase in frequency compared to this, or a decrease in frequency compared to this side? This one is a decrease in frequency compared to this side. The wavelengths are longer, crest to crest. So the next thing we're going to talk about are how these wavelengths influence and what is the greenhouse effect. So this is where I'm going to start drawing stuff. Okay. Here we go. Greenhouse effect. You will draw it. Drawing is part of notes, so good question.
Where should we?
Well, where do you have blank space on your paper?
Just draw it wherever.
Yep, you can draw it on that paper. On the other side, remember I said you could cross out where it said the layers of the earth. You can use that space. Okay. Or you can get out another blank piece of paper and draw it on there. Okay? All right, so here we go. We're going to go with the greenhouse effect. We need the sun. And from the sun is our electromagnetic waves. And then down here, we have the earth. So from the sun, 93 million miles away to Earth, we have these waves that are emitted. These waves that come from the sun, we're going to specifically talk about UV waves or rays. You might hear it as rays. I say that a lot. So we have these UV waves, and they're coming down. This one's going to come all the way down to Earth and hit the ground. So I need to know what I'm talking about, so I'm going to put UV. And then I may forget what that means later, so off to the side, I'm going to remind myself for now. So UV stands for ultraviolet waves. Okay. Anyone have an idea what the greenhouse effect is? That wants to share? Go ahead.
Like the heat gets trapped inside of it, kind of?
Right, the heat kind of gets trapped inside of our atmosphere. Go ahead.
The ozone layer doesn't protect from all of the rays, so some of them come into the state.
Right, so some of the UV rays actually make it through the ozone, and we'll talk about that in a little bit, and come down to Earth, and some of them stay here for a while anyway. So we'll talk about that. So when the UV rays come out from the sun, they hit the Earth, in this example, and they elongate. As they elongate, they're turning to a different kind of wavelength, because we can see the frequency has changed, and these are changing to infrared waves. Infrared waves, Carrie, make things hotter. Now, this infrared wave can hit a cloud, let's say, and it comes back down. And it goes back up. And let's say it hits some greenhouse gases. We'll say what those are. It's going to come back down. Let's say it hits a tree, because it doesn't have to hit the ground, okay? So it hits a tree, and then finally, woo, it's out of here. That's good at this point, because it's getting warm in here.
What are the dots?
Yeah. The dots are greenhouse gases. So we can write, we'll write greenhouse gases. So the UV waves come down, hit something, elongate, change into the infrared waves, and start to heat up. Which is good, because what if they just left right away? It'd be kind of chilly, right? So we'll kind of think about it like a car. You guys have all experienced the greenhouse effect in a car. So there's my car. So the car is just like the greenhouse effect. If it's a hot day and you go in to get in your car, what happens?
It's hot.
It's hot. Sometimes it's so hot you can't even touch the steering wheel. Okay? Now, let's go, it's February and it's super, super cold outside and it's sunny and you go into your car, what is it? Warm. And you're like, oh, thank you. So a little bit of heat, a little bit of greenhouse is good because it keeps us warm. It allows us to wear t-shirts and, you know, survive with this temperature. But just like anything else, too much of a good thing can go wrong. It can get too hot. So you guys have all experienced the greenhouse effect just like in a car. So what we want to do is make sure that we have a system in place in our atmosphere in which this heat can escape. Because if this can't escape, what still keeps coming in? Heat. Heat and heat and heat. I can't escape heat. So it's kind of like if we turn the heat on in this room, so it's 65 to 70, it's like, oh, nice. But we're not turning the heat off anymore.
It's like hot yoga.
Okay? It's like hot yoga and then hotter than hot yoga. Hot yoga times 10. And then eventually we're not able to survive. Not all species will be able to survive in that heat. So we need to maintain that stable cycle in which the wavelengths can come in, warm up, and then leave before it gets too hot. Okay? So let's define the greenhouse effect. See if this pen works. So what's happening? The UV waves change by increasing wavelength to infrared which increase temperature in the atmosphere. We'll say atmosphere for now. specifically the atmosphere layer we're in, which is the troposphere. But we'll get into that a little bit later. There's consequences of too much heat, and that's when you guys hear about global warming and climate change and this increase in temperature. That July was the hottest July on record in the world, and I think this year was the hottest ever recorded. So we're seeing an increase in temperatures, and we're seeing some consequences of those. Melting of ice caps, increasing of temperatures, flooding of islands, people having to be relocated, and then there's possible ramifications of that in the future. So we're looking at the world climate change, etc., to try to work on those things. And one of the major things we're doing is to decrease our two major, especially one, but we have two major greenhouse gases that we're going to talk about. If you think you know what those two major greenhouse gases are, write those down. Question?
I saw this video that said that in India it's getting so hot that when they're walking on the roads, their shoes are starting to melt to the road because it's so hot.
Maybe. I haven't heard that, but I know they have had major heat waves. Last year it was like 120, 125 degrees heat waves. And
yeah.
So
and it was videos of people walking across the street and their shoes were legit like staying on.
Sticking, yeah. That's not a good day. Go ahead.
Whenever I lived in Las Vegas, like over time, like holes formed in my shoes because it got so hot on the ground.
Wow. So maybe we need to make our shoes different. Or we could look at minimizing these greenhouse gases. That might be better. But it is getting hotter, and you guys are starting to see that. So let's talk about the two major greenhouse gases. What are they? Anybody? Okay, carbon dioxide. There's more greenhouse gases, but we're going to focus on these two. Not nitrogen, thank goodness, since our atmosphere is 78% nitrogen. So CO2, and then it's carbon dioxide, if you're not sure what that is. Write it down if you don't know. Now, carbon dioxide, where is that coming from? Yes?
Our cars and like factories.
Right, so mostly the burning of fossil fuels, which is oil. And the main culprit, something that we can do to help limit that greenhouse gas, is the cars, okay, exhaust. So combustion engines are a major contributor to carbon dioxide. We breathe out carbon dioxide, but that's part of the cycle, and we have plants and ocean and soil that actually is a carbon sink, and so it can actually uptake a lot of that carbon. Be thankful for the ocean, because it uptakes a lot of that carbon and takes it out of the atmosphere. One thing we can do is stop contributing to so much carbon dioxide, and one of the things that you guys have control over somewhat, especially as you get older, is the emission from vehicles. So when we're talking about fossil fuels, that's oil. Oil comes out of the ground, right? And so what makes up plastic? How's plastic made? Petroleum. What's petroleum?
Isn't it like from oil?
Oil. So all plastics are made up of oil. So one of the things you can do is stop buying so much plastic, okay, and recycle. So let's look on my desk what I've got. I got plastic, 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 plastic. So you can substitute oil, 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 oil. I mean, there's plastic everywhere, and I try to be aware of it. So one of the things we looked at is we were calculating density the other day, and we're looking at styrofoam oil. And then we were looking at the packing peanuts, right? So we've got packing peanuts.
There's more.
And there's more right here. So this packing peanut.
Oh, okay.
Just eat that.
Does that have cornstarch in it?
Oh my
It's made from.
This packing peanut is not made from styrofoam or petroleum anymore. They're making packing peanuts from corn, and they're learning through engineering in different ways to spin it and aerate it, so now it dissolves. Okay? So not all packing peanuts are corn-based. So if you put one in your mouth and it doesn't dissolve, then it's not corn. If you have an allergy to corn, of course, don't eat it. Yes?
Does it taste good?
No, and there's really no taste.
So it tastes like water.
It's just like, bleh. If that's a description of taste, bleh.
So it's like.
Okay, next. What is the other major greenhouse gas? You do it. I'm doing it right now.
Breathe.
What did I breathe out?
Water vapor.
I breathed out carbon dioxide and
Water vapor.
water vapor.
Water vapor.
You can just draw a little heart. I love science, right?
Oh.
So if you breathe on glass, you can draw it on the glass because there's water vapor, and that's what you're exhaling. So water vapor. And that's a gas. Now this is starting to get the vicious cycle. So if we have too much CO2, that's the little dot, that's one of the greenhouse gases that basically when the infrared wants to escape, the greenhouse says, go back. And then the infrared tries to get out again, and it's like, go back. And it starts getting hotter and hotter. So when it gets hotter and hotter, water gets more energy in it, and because most of the earth is covered in water, when you have more energy, liquid water turns to gas. It now becomes a greenhouse gas. It's now more of the stuff is in the air, having those infrared rays go back down, hotter, 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 more water evaporating, hotter, 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 more water. Okay, water vapor. So it becomes this vicious cycle. So that is why these are on the top of the list for the major. There are other greenhouse gases, and you'll hear about them, methanes, any of the propanes, butanes, etc. But these are the two right now, especially this one for humans to be able to try to get their carbon emissions as low as possible. Okay. Questions on that? Now the next thing we're going to do is talk about the ozone. So if you look at your questions on your paper, it says, which type of EMR is involved with the ozone? And that's what we're answering right now. EMR. Ooh, I'm going to start with the sun. So I've got the sun, and I've got the UV rays coming to Earth. Or not. So what happens is we have the ozone. Ozone is 3 oxygens. So it's written like this, O3. How we usually draw that in this class is 3 oxygens hooked together. So I'm going to put an equal sign. So the O3 is going to equal the 3 oxygens hooked together. Now what happens is this UV wave will come down and hit ozone. Now oxygen does not like to be alone. If you have 1 oxygen, bad. It will basically attach itself to anything that comes along as fast as possible, because when it is alone, it is freaking out. So what happens is we breathe oxygen, O2. Okay. Ozone, I'm going to put that up here, is O3. Now the ozone up there is when the UV ray hits it, number one, we'll just do them in steps, the ozone separates. Step 2. So you're going to have the UV and it's going to separate. 2 are going to stay together and 1's going to go away. That is just enough energy absorption elongation to get that back to space. And then as soon as those 2 lose that 1 oxygen, it is back. Bam. It does not like being alone by itself. It hooks right back up. Ozone again. Nice. So it's very recyclable. It's a very stable environment in which that we're constantly breaking apart, putting together, breaking apart, put together. Bam, 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 bam. Okay? So now if the UV comes down and makes it through, because they don't all get pushed away, but makes it through to Earth, we would have way too much UV making it down to the Earth. One of the consequences, not just with the, imagine the greenhouse gases, okay, being able to trap more UV. That's like instead of this room having 1 heater, if all these UVs, maybe we'd have 20 heaters in here. So you'd be getting a lot more UV waves down into the troposphere where we're at. Some consequences of that, here I am, trying to enjoy my day, and I'm getting hit with so many UV that one of the consequences then would be sunburns, right? There I am getting a sunburn. Doesn't take me as long as maybe some of you. So there are some consequences of that, just not just with the increased heat, increased greenhouse effect. We're looking at sunburns, increase, and can lead to increase in skin cancer or cancers. So there are a lot of consequences to that. So the ozone does a really good job protecting us from those things. So when you're looking for a new bumper sticker to put on your car, maybe thank you ozone, or we love the ozone would be a great thing, because it does a lot to help protect you. There have been holes in this ozone and breaking down of the oxygen, so other things have been up in our atmosphere, so this oxygen, instead of going back to the other 2, it hooks up with other things. Okay? And so we've gotten rid of those gases, made some of those illegal, so that they don't float up into this portion of our atmosphere and prevent those oxygens from hooking back up to make ozone. Trying to heal the ozone holes that we've had, because we need that protection layer. Questions? Okay. So the next thing we're going to do is I want you to go ahead and look at your handout we passed out. Okay, you guys have a handout that looks like this. And I'm going to flip mine around. Let's go through this real And then you'll see what your expectations are for this. When we're looking at this diagram right here, this is your number 15. Nice and quiet, please. Right up here we have the visible spectrum. The visible spectrum are colors. And when we're looking up here, red is going to be the color that goes in this box. If you guys remember Roy G. Biv, once you see red, you can figure out the Roy G. Biv and what order those colors will go in. How do I know it goes on this side and not this side? Because I'm going to look down at my electromagnetic spectrum. These are the longer wavelengths. The longer wavelengths are associated with the color red. So the red wavelengths, the radio waves are long. Are long. Okay. So if you get a quiz or test and it's flipped, and the long wavelengths are on this side, you would start red here. And it would go Roy G. Biv, backwards. So always when you're looking and you get this diagram and you have a wavelength for you, make sure the red aligns with that longer wavelength. And we'll go into that more later. So that's your visible spectrum, but that's not all that's on the spectrum. In fact, it's a very tiny portion of it. We're going to go with the general parts of the electromagnetic spectrum, and off to the left we have radio waves, which are very long, to the microwave, which you guys are familiar with microwave ovens, and cell phones use microwaves. Infrared, that's heat. So you have like heat lamps. If you guys have chickens, you could use a heat lamp to keep them warm, or if you guys have snakes or stuff like that, you'll buy heat lamps, okay? Shh. And then you have your visible spectrum, and then ultraviolet. We talked a lot about that today. And X-rays, see the frequency? It's changing. The type of energy changes with the wavelength. And then gamma, very small, microscopic, lasers. They do brain surgery. They're very small. They can use gamma knives so they can cut. And so they heal faster, less scarring. And they can get into very particular parts so they don't cut into other areas of the brain. So they're used for lots of different things. If we look down here at the waves, we're going to add frequency. What type's over here? Low. Compared to this side, high. Wavelength, low. Oh, sorry, long. Sorry. Compared to this side, short. And then we're going to add energy at the bottom. So on this side, you have low energy. And over on this side, you have high energy. So what you're going to do while I play the rest of the video on Mount Everest is you are going to fill yours in. I've got colored pencils today, and I will keep them out for you guys as long as you put them back in the right spots. The colors all go together. You can see in the back. And so what I want you to do is color in your rainbow. Indigo, they're kind of trying to get rid of. But right now we have indigo, and it's basically a combination of violet and blue. So you can I overlap the colors on mine. And then I want you to go in where you wrote the words and give an example. So I drew like a walkie-talkie here. And then you're going to come up with examples. X-ray, that's a rib cage. And then this is a laser. So sometimes I'm not a very good drawer, so I have to actually tell you what it is as well, because we're not all artists. Okay. So you need to have these all filled in with pictures and all the words on here and colored in nice and tidy like. And you can be doing your coloring and your pictures while we're watching the rest of Mount Everest. And you should have this done by the time you come to class next time. And you should study for your density retesting option to pick up points. Questions? Okay, just send one person from your tables to go get colored pencils so we don't have everybody up to date.